Now it took quite a while after we learned that one, what I call graph altitude, and I call them altitudes because they go this way, and let me clear up in advance one piece of confusion. We've got a trapezoid, okay, the region underneath the line segment connecting these two nearby points, and whatever the curve happens to be, if the points are nearby enough, the curve, if it's a smooth curve, is going to be very much, very nearly linear. We've got a trapezoid, and I'm going to draw what I call the altitudes of this trapezoid. Okay, now this is clearly a trapezoid. You got two parallel lines, and then two other sides. In this case, this side of the trapezoid is perpendicular to one of the parallel sides. Now, the altitude of a trapezoid is actually defined geometrically, for good reason, to be the distance between the parallel sides. So the altitude of the trapezoid would be measured this way, and this thing that we see as a width is actually geometrically the altitude of a trapezoid. So forget anything you know about formulas for areas of trapezoids. You don't need them. I'm talking now about graph altitude, and graph altitude is this. Now these are actually bases of the trapezoid. Now that I've said that, understand that there's a difference in terminology here, and forget that these are bases. These are what I call graph altitudes, just because they go up this way, okay? And they represent the values of the kinetic energy, okay? The initial kinetic energy is just how far it is from here to here. That distance represents the initial kinetic energy, and here it is. The final kinetic energy is, well, it goes from here to here. Here's your final kinetic energy, here's 0. So this distance represents your final kinetic energy, or this upward displacement represents your final kinetic energy. Okay? So here we have the final kinetic energy. Now, where's the average of the initial and final kinetic energy? The question I posed in class is, how do you construct, based on this picture, a line segment that represents the average value of the kinetic energies? Okay, one of the first answers I got was, well, this. Well, that's not the average of these altitudes. This is smaller than either of these altitudes. It's clearly not the average of the altitudes. Now I got a correct answer. I said, well, you take half of this and add it to the initial, and you get the average. And that was a good answer. It's not the most elegant way to see the connection, but it's an important thing to understand. Also, that if you subtract half of the change in kinetic energy from the final value, you're going to get the average value. But how can I construct that on this graph? Okay, I could actually construct based on the idea that I just mentioned. Okay, but where would it appear in this graph most logically? Well, really, the average value is halfway between the initial and the final. I've got a straight line that goes from here to here. If I go to the midpoint of this line and drop the altitude down here, it's going to be halfway between this one and this one, so it's going to represent the average value. Also, if I cut this trapezoid through that midpoint of this segment, I'm going to have a triangle up here that I could slice off, turn upside down, and add down here, and that construction would show me that the rectangle, whose altitude, if you will, is the length of this segment, and whose width is this. Okay, that, in other words, this rectangle here, bounded here, has an area that represents the average value of the final kinetic energy multiplied by the change in x here. So that the area of the trapezoid is the average kinetic energy, because, of course, we're doing the average value of the kinetic energy times delta x. Now, before anybody accuses me of misleading anyone. If there's a second derivative, non-zero second derivative across here, in other words, if your function isn't a straight line, then chances are that you don't have the exact average value of your kinetic energy here. Okay? The average of your initial and final is not the actual average. But these are nearby points, and if they're nearby enough, the difference between the actual average and the average of the initial and final becomes insignificant, and you need to think about and understand why. And you should relate that to what you should understand about the meaning of the integral and the fundamental theorem of calculus and how it's proved. Okay. Anyhow, the area is your average kinetic energy times delta x. Now, unlike the interpretation of the slope as the average of your net force, which indicates that the derivative of the kinetic energy function with respect to position is your instantaneous net force, okay, this doesn't have a physically meaningful interpretation in most situations. Okay, so this is actually a pointless exercise. It doesn't really give us a lot of information in general about energy and force and so forth. So when you do this, you don't always get something meaningful. Now, we're going to interpret the same things in terms of the net force versus position graph and draw some conclusions and see what's important here.